The Dredgemaster hydraulics are enclosed in an EMA 12 enclosure protecting the hydraulic components from moisture, dirt, and dust. The hydraulic enclosure is often mounted in the area of the hydraulic pump supplying hydraulic oil to the Dredgemaster system and the hydraulic reservoir to provide return oil. Under the hydraulic enclosure is a hydraulic hoses for pressure, return, and cylinder operation. The far right-hand hose is a pressure hose coming from the pressure port of the hydraulic pump. This hose is attached to a high-pressure filter. Next is the pressure gauge used to monitor the main pressure coming from the pump. The second hose from the right is a hydraulic return line. This hose directs oil back to the hydraulic oil reservoir. The second hose from the left is a hose that attaches to the open side of the hydraulic cylinder on the butterfly valve located under the water. The left-hand hose attaches to the closed side of the hydraulic cylinder, controlling the butterfly valve located under the water. Both the hydraulic open and closed hoses have lockout valves attached to them. These valves must be locked out anytime repair or maintenance is being performed to the hydraulic cylinder or to the butterfly valve. This is to prevent any accidental opening or closing of the butterfly valve in the event a person's hands are near the hydraulic cylinder or the butterfly valve. Closed position. Closed position. Lock will be attached to these holes. Open position. The high pressure filter requires replacement periodically. We recommend replacement within the first 2 weeks of operation and every 6 months to 1 year after that. In the event a hydraulic component should fail, causing contamination to the hydraulic oil system, this filter should be changed immediately after the repair is made, and may require frequent changes to aid in the cleanup of the hydraulic system. Never attempt to clean the filter, and always replace the filter with a new element. Changing of the filter element can be performed by using 2 wrenches, an 1 3/8" wrench on the top side and an 1 1/2" wrench on the bottom side. Remove the filter housing. There is a spring on the outside of the filter. There's also a spring on the inside of the filter. Remove those. Install a new element by inserting the spring back on the inside and the spring on the external side. Mount it back on the cap. Make sure the O-ring and the cap is in good condition. There's also an O-ring on the inside of the element. Make sure that that filter is also in good condition. Both this O-ring and the inside O-ring comes as a kit with the element, so they are with the element for replacement. Simply slide the element back in place and start the threads and retighten. After the filter has been hand tightened, finish tightening the plug till just snug, and that's all there is to changing it. Inside the enclosure are the following components: a proportional valve, a pressure compensated valve, a check valve, and a base plate with a pressure regulating valve mounted at the base of the base plate. A variable electric current to either the open or the closed coils of the proportional valve directs oil flow to the hydraulic cylinder attached to the butterfly valve. 2 hydraulic pressure transducers provide feedback to the Dredgemaster system, providing pressure readings during open and closed periods of the hydraulic cylinder. A temperature transducer continually monitors the hydraulic oil temperature, and when a 30-degree temperature fluctuation occurs, it triggers the Dredgemaster to recalibrate the hydraulic cylinder, giving the operator accurate feedback of the hydraulic cylinder's position on the Dredgemaster screen. In the event a hydraulic pressure transducer should fail, easy replacement of the transducer can be performed by removing the wire connection on the panel and loosening the fitting at the base of the pressure transducer. And now I'm going to take the new transducer, install it back on top of the fitting. Okay, finish snugging up the fitting. Okay. I'm going to rotate the electric plug until it snaps in, and then continue to turn it tight. Removal and replacement of the main control harness is very simply done by unscrewing the nut and pulling it away from the unit. To reinstall the unit, you push it in until it snaps and continue to turn the nut in until it's tight. The vacuum and pressure manifold is usually mounted inside the dredge cabin. The manifold on the left side contains a vacuum transducer, an on-off ball valve, and a drain valve. A vacuum hose coming from a standpipe mounted on the suction pipe ahead of the pump is attached to the bottom elbow. The top elbow has a plug in it and can be removed and replaced with a line going to a manual gauge, vacuum gauge if desired. During operation, make sure the ball valve handle is positioned down or in its open position, so vacuum can be introduced into the vacuum transducer. Periodically, the vacuum line and manifold require draining or cleaning. This can be performed by opening the drain valve during periods of high vacuum and tapping on the end of the drain valve with a finger. An indication of a line becoming plugged will be indicated by a sluggish vacuum response on the vacuum gauge on the Dredgemaster screen. If the vacuum line or manifold becomes plugged, the operator will notice no change in the vacuum gauge on the Dredgemaster monitor. This may indicate a plugged vacuum line or manifold. Compressed air may be required to remove the plug. First, close the ball valve below the transducer. Open the drain valve. Attach a blowgun with a rubber tip to drain valve and blow air into the vacuum system to clear plug. After removing the plug, close the drain valve and open up the ball valve. In the event there is no reading or no response in change displayed on the vacuum gauge on the Dredgemaster monitor, a failed vacuum transducer may be the cause. To replace vacuum transducer, remove electrical plug from the main harness. Install a new transducer, making sure to use a sealing tape or paste on the threads of the transducer before installing it. Alright. Plug transducer wire back into vacuum harness wire. The manifold on the right-hand side contains a discharge line pressure transducer, an on-off ball valve, and a drain valve. A pressure line coming from a discharge standpipe located on the main pump discharge line is attached to the lower manifold elbow. The top elbow has a plug installed and can be removed and replaced with a hose going to a mechanical pressure gauge if desired. During operation, make sure the ball valve handle is positioned down or in the open position so pressure can be introduced into the pressure transducer. Periodically, the pressure line and manifold require cleaning. This is indicated by a sluggish response of the pressure gauge on the Dredgemaster monitor. The operator must first shut down the main pump, then close the ball valve, open the drain valve, and introduce air into the drain valve. After a plug has been freed, close the drain valve and reopen the ball valve. In the event there is no reading or response or any change in pressure on the pressure gauge of the Dredgemaster monitor, a pressure transducer may be a cause of failure. To replace the pressure transducer, remove pressure transducer wire connector from the main harness. Unscrew the pressure transducer from the ball valve. Make sure to put sealing tape or thread paste on pressure transducer before threading new pressure transducer onto ball valve, like previously shown on the vacuum transducer. Install pressure transducer connector into main harness connector as shown. The Dredgemaster electronic enclosure is generally mounted in the dredge cabin. It houses the main electrical components of the Dredgemaster system. On the front cover is the on-off switch and the power indicator light. On the side of the enclosure is the master switch, or also can be used as a lockout switch by turning the switch off and removing the key. This also must be done anytime service is being performed on the valve cylinder or the butterfly valve, which is mounted on the dredge suction pipe. Next to the lockout switch is a 3-amp circuit breaker. In the event an electrical short should occur, the circuit breaker will trip, preventing current to be supplied to any of the Dredgemaster electric components. Once the shorted component or wire is repaired, it will be necessary to push in on the button of the circuit breaker to reset it. This will allow electric current to flow to the Dredgemaster electrical system. On the bottom is the main electrical harness connector and the monitor harness connector. Inside the enclosure is a PLC unit, which contains several components. First is a PLC base plate and electrical power supply. All Dredgemaster PLC base plates operate on 24-volt DC power. The top terminal is 24-volt DC plus, and the second terminal is 24-volt DC minus. The next component is the CPU module. This contains the logic software of the Dredgemaster system. This unit can only be programmed by factory personnel in the event of failure. In the event of a CPU failure, first thing to do is turn off the power. Next, you'll need to disconnect the communication cable by unscrewing the 2 top and bottom screws, pulling out the cable. Next, pull out the top and the bottom tabs, and then simply gently pull the module from the base plate. To replace a new CPU module, simply insert the module into the base plate, push it in until you hear a slight snap, push the two tabs in, hook up your communication cable, tighten the top and bottom screws, and turn the power back on. Inside the CPU module there's also a battery to back up the data. This battery should be replaced every 2 years. To replace the battery, simply push down on the tab and gently pull the battery holder out and pry the battery out of the holder. Insert a new battery into the battery holder. Push it in until a slight snap is felt. Rotate the holder in, push down on the tab, and snap it in place. The next module is the analog input module. This module gathers a 4 to 20 milliamp value from the pressure transducer, the vacuum transducer, the velocity meter, the temperature transducer, the hydraulic open and close pressure transducers, and, if installed, the optional depth transducer. It sends this information into the CPU module so that these values can be displayed on the Dredgemaster monitor. The next module is the analog out module. This unit sends a 0 to 5 volt DC to the open coil of the proportional valve to allow the hydraulic cylinder to open the butterfly valve. This voltage is displayed on the front panel of the enclosure. When the valve is opening, you'll see the meter go to the right, or a positive voltage, each time the valve opens. When the valve is closing, the analog output module sends a negative voltage to the proportional valve, going in a negative direction, sending voltage in a negative direction to close the valve. In the event there's a failure of the input module or the output module, both these modules can easily be replaced. The first thing that needs to be performed is to turn off the power. Second thing that needs to happen is on the bottom there's a little tab that you push up and you snap the front cover off. The next thing is you squeeze in these two tabs here and gently pull the electrical terminal block away from the module. Simply snap out the top and the bottom tabs and gently pull the module out of the base plate. Just simply reverse the procedure for module replacement. The unit below the PLC is the electronic control amplifier for controlling current to the open and closed coils of the hydraulic proportional valve. Never attempt to change any of the screw settings. These are all set specifically for each individual Dredgemaster system and should never require adjusting. There are two diodes on the positive and negative wires supplying power to the PLC. These prevent electrical damage from occurring to the PLC in the event the main electrical system should accidentally be reversed. For example, someone hooking up the wires to the wrong battery terminal while changing out a battery. If the PLC CPU light and run lights are not illuminated when there is power to the rest of the Dredgemaster system, there may be a failed diode. To check the diode, remove the front cover of the power supply. Next, you'll need to loosen the two screws holding the diodes. Next you'll need to do is remove the diode from the electrical connector by simply pulling it apart. A multimeter will be required to test the diode. Turn the dial of the multimeter to the test diode position. Then place the positive and negative leads of the multimeter on each end of the diode. As you can see, there is no connectivity in this direction through the diode. Reverse the leads of the multimeter. Now you can see we have 0.583 amps going through the diode. This diode does test okay. Next you'll need to do the same procedure with the negative diode, making sure that you do have connectivity at least one way through the diode. After replacing the defective diode, simply turn the power back on the unit and verify that we do have power with the power light on the CPU and the run light does light. This is the main screen of the Dredgemaster system. Across the top we have the version number, we have the ability to select different recipes, we have the date and the time up here. It also displays what your vacuum is, what your velocity in the pipeline is, and what the discharge line pressure in the discharge pipe is. Over on this side we are displaying the position of the valve. On the lower portion of the screen we have an auto and a manual button here. We have the ability of an option of being able to give you the angle and the depth of your ladder. We're also displaying the temperature of the oil and the hydraulic pressure. We have various options we can display in here, like pump RPMs, chain RPMs, cutter RPMs. This is a calibration indicator. We have a help menu and a setup button to go into other optional screens. As we can see, the vacuum screen is broke down into different colors. The aqua color represents a lower vacuum value. This area in turquoise represents low production. If you have low vacuum, usually that represents low production. Our green area in here represents good production. In other words, we're starting to maximize the dredge's capabilities of pumping material to the plant. Our yellow area is what we call our caution zone. That is an area, if you pump at that high of a vacuum for very long, your percent solids in your pipeline start to increase to the point where you would start to endanger plugging the pipe. In the yellow zone area, that's where we want to start to step the valve open, as we'll demonstrate shortly. The red zone is an area that is what we call our emergency zone area. That's if we have a cave-in and all of a sudden our vacuum spikes high. We want to open the valve immediately. We don't want the valve to step open. We want the valve to rapidly open up. The velocity is also in 4 different colors. The aqua is represented on this side of the scale. If we have a rapid velocity, or feet or meters per second, then there's probably not much material in the pipeline, so we're representing that by an aqua color, in other words low production. The green area is a zone that will represent good production going to the plant, but it's an area where we do not have to worry about the pipeline plugging. Again, the caution or the yellow zone area, as you can see here, is the area where we're starting to get a high enough percent solids in the pipeline that if you do continue to pump at that feet or meters per second, then the pipe would have a possibility of endangered plugging. Again, if we get too slow, we have our red zone here on the left, and therefore we immediately open up the valve instantly when we enter into the red zone area. The pressure gauge is a little different, and all we have is 2 colors. We have a red zone, a green zone. The green zone is the area that you want to set where your pipeline discharge line pressures normally operate in. As we can see, we have a red zone to the left of our green zone. If a pump starts to cavitate, what happens to the pump is that it starts to recirculate material inside the impeller. When this happens, the pressure usually drops below a set point. If that recirculation or cavitation issue occurs, we're going to sense that drop and we'll get into this red zone area. When the valve goes into the red zone area, it's immediately going to open the valve fully. If it didn't catch the red zone on the low side, once the material catches hold inside the impeller again, it usually all of a sudden tries to discharge a bunch of material out the discharge of the pipe. When this happens, all of a sudden the pressure will spike up. When the pressure spikes up, then we're going to experience a high discharge line pressure. And when that high discharge line pressure occurs, then we will definitely open up the valve on the high side. So it's important to set this green zone in areas where your normally pipeline discharge line pressure or bar is going to be running at. And then if you do experience a cavitation issue, we want it to be able to catch it hopefully on the low side first. If not, we want to be able to catch it on the upper side of the upper scale of the red zone. This is the valve position. This tells how far the valve is closed or open under the water. This is what we call our freshwater production valve. 0 down here at the far left represents closed, and if the valve moves over to the high side over here, it would be fully open. As you can see, as we step this valve open, our blue line starts to increase. The valve is starting to open up. It will continue to open up. We also have an opening indicator light here. If the valve needs to close itself back down, we are starting to see a closed. The valve starts closing itself, and you can see a closing light on the left side there. The valve position also gradually drops or increases depending on which way the valve is moving, so you can see your valve position opening up here. Let's look at the color zones on our vacuum gauge. As we all know, different dredges and different deposits require us to be able to have different parameters set in there at the point where we want the valve to open or where we want the valve to close. So all 4 of these colors zones are adjustable, as we'll show you how to do here in just a second. Okay, let's take a look on how we adjust these color zones. First of all, we're going to touch our setup button in the lower right hand corner of the screen down here, and here's our gauge set points. This first column is our vacuum, so let's focus on our vacuum first of all. The first item here is our rapid open. This is the vacuum setting that determines the start of our red zone. In other words, our emergency zone, our red zone. Currently, we're setting at 25 inches of mercury is where we have it triggered to open up the valve rapidly. Let's say, for example, you want to change it to 24 inches of mercury instead. You simply enter in 240, and we have 24. We hit enter. Now our valve is going to rapidly open up at 24 inches of mercury or millimeters of mercury, either or. The next position is our yellow zone, where we want to start the yellow zone. In other words, where we want to start to step the valve open to introduce fresh water into the suction side of the inlet pipe, vacuum pipe. Let's say we want that to be at 20. We want that to start opening up at 20. So we're going to enter in 20 here. We're going to hit enter. Now our valve will start to step open at 20, in this case inches of mercury, or could be millimeters of mercury. Our slow close set point is where our turquoise and our green zones come together. Currently we're set at 18 inches of mercury. Let's change that down to maybe 17. Simply touch and enter. Now we've made that change in there. Now since we've made that change, we need to press this accept new recipe parameters. We are currently running on recipe number 1. So to make that change that we just did, we're going to touch that. Now that set those parameters to recipe number 1. We're going to go back to our main gauge right here, touching the main button, and boom, you can see how all our colors just changed. So now, for the valve to start opening up, we have to get at 20 inches of vacuum for our valve to start opening. Once we get less than 20 inches, we're back into our green zone and our valve can start closing itself back down. So this is the set point between our green, which is closing the valve, and the yellow area, which is stepping the valve open. Okay, we demonstrated the stepping open when we went into the yellow zone, how the valve will step itself open. Next we want to demonstrate how we get into the red zone, how the valve will instantly open itself. In an event that you have material starting to cave in on your cutter or your suction of the dredge's ladder, we don't have time for this valve to step itself open. We'll cavitate the pump and highly endanger the possibility of plugging the pipeline. So we're going to demonstrate how our vacuum is going to start rising and then get into the red zone. You're first going to see the valve start to step open while we're in the yellow. As soon as it hits that red zone, you're going to see the valve immediately open itself up. We'll demonstrate that by starting the valve. We're in the yellow zone here. Our valve is starting to step open. Okay, our vacuum is still climbing. We're now in the red zone. As soon as we hit the red zone, our valve fully opened up, preventing cavitation of the pump, and we instantly got a full amount of water from the freshwater production valve to eliminate any possibility of a pipeline plug. Once the vacuum starts to drop, or in other words, we're starting to pump the material away from the cutter or the suction of the dredge, our vacuum starts dropping. When the vacuum drops back into the green zone area again, we're into the green zone, our valve can now start stepping itself back closed. It'll continue to step itself closed until it's fully closed, or if our vacuum starts to increase again back into our yellow zone, you notice the valve starts reversing direction and starts to open itself up. Once it lets in enough water in the suction side, it starts reducing the vacuum. We're back into the green zone again, and we can now start continuing to close the valve. The valve may continually go back and forth in this area. If you have a lot of material in front of the suction of the dredge, this valve may continually open and close automatically on its own until the vacuum has dropped down into the green zone and remains in the green zone for a period of time to allow this valve to fully close. The thing we want to stress is the operator needs to make sure he sets this green zone area to areas of vacuum that do represent good production. The yellow areas need to represent the vacuum levels that are starting to be a danger area or a caution area, that if he stays pumping in that zone for very long, that's where we want the valve to start opening up. So it's important that this yellow area gets set correctly as well. And also, if we do run into a high vacuum situation where we have a cave-in, that at a point just before we start to cavitate the pump, we want to make sure we set our red zone. If your red zone is set too high, you're going to hear the pump cavitate before the valve actually opens up. In that case, you're going to want to set your red area a little bit lower so that we prevent the pump from cavitating. The turquoise and the greens area is the area that determines where our green zone or our production area is going to be at. So that is also critical that you set that, so our green zone is where you want it to be to represent good production. The velocity also represents 4 colors. As we explained before, the turquoise represents low production, the green is good production, the yellow is caution, and the red area is starting to get yourself into serious trouble. As our velocity starts to slow down, we have more material or a high percent of solids in the pipeline. In our green zone area, of course, the valve remains closed. Once the material starts slowing down into the pipe and we enter into the yellow zone, we are now starting to open up the valve. The valve is opening. We're in the yellow zone here. Once we get enough fresh water introduced into the pipeline, our velocity starts picking up, starts speeding up. We're back into the green zone. We can now start to close our valve back. Alright, let's demonstrate the velocity going into the red zone. If our velocity starts to slow down, of course in the turquoise area is low production, our valve needs to remain closed. Our green area is our production, where we're maximizing our production but yet not getting into trouble. Our valve is also closed. As soon as you can see, our velocity in our pipeline is starting to slow down. Once it gets into the yellow zone, it's starting to open up the valve, but our velocity continues to drop. We've got a lot of material in front of the cutter. As it starts to continue to drop into the red zone, boom, we're into the red zone here. Boom, our valve now fully opened up. So now we're letting as much fresh water introduce into the suction side of the pump, which in turn is reducing the percent solids in the pipeline. Once the percent solids in the pipeline starts to reduce, our velocity starts to pick itself back up again. As you can see, the velocity is starting to pick up higher and higher, and now it's back into the green zone. And once we're into the green zone, our valve can start closing itself up. Okay, we're going to show you in the setup screen how to change your velocity parameters. First thing you do is you touch your little setup button in the lower right hand corner. We now have our low velocity set points. Our rapid open is set currently at 12 feet per second, or could be meters per second. If we want to change that, let's say we want our velocity our valve to rapidly open at 13 instead of 12. We're going to enter in 130 to give us 13. Hit enter. Valve now will start to rapidly open at 13 feet or meters per second. The next is our slow open. This is where the valve is going to start to step itself open. Currently we're set at 14. Let's change that to 15. Let's say we want the valve to start opening a little quicker at 15. And then the area where our green zone and our turquoise zones meet is this area right here. And what's going to change that to 17.5, for example. Hit enter. Since we made this change, we're on recipe number 1. We're going to touch or press to accept new recipe. We're going to go to the main screen, and now you can see our parameters just have changed here. So now we have to get down to 15 feet per second or less for a valve to start opening. And once we get to 13 feet per second, our valve will rapidly open, as you can see. So we just changed our set points of our color zones by just simply touching the setup button and going to the gauge set point, which is right here for the velocity. Okay, the next gauge we're going to look at is our pressure gauge. Again, our green zone area is an area where we have good production, not endangering the pipe to plug. So as you can see, our valve is closed. Let's start to simulate a condition where the pump is starting to cavitate for whatever reason. our pressure is going to start to drop, and it probably is going to drop rapidly. And as soon as it gets into our lower red set point, our valve immediately opened up. This prevented a cavitation from happening at the pump. So you want this set point between your green and your red area to be just before you start to cavitate a pump. So we eliminate that from happening. Once we got enough material back in the suction side, our pressure is going to come back up into a normal range. As soon as that happens, our valve can start closing itself back down. Let's make an assumption that we started to our pressure started to drop because we have a heavy load in the pipeline. Our pressure dropped, but it didn't quite get down there low enough to get into the red, and then all of a sudden, boom, it spikes up, catches hold inside the pump, it spikes up into the red zone on the top side, again fully opened up the valve. The key is set this green zone area here where the valve is not going to open up fully like it just did unless you have a real issue going on inside the pump. We don't want the valve to continually rapidly opening itself back and forth in these red zones without a real need to having to do so. To change our set points on the pressure gauge, go into the setup screen. Our low set point pressure is currently set at 50 psi or could be in bars. Our high pressure set point is currently set at 75 psi or could also be in a bar. Let's say we want this to be 40 psi before we want that valve to rapidly open. We simply enter in 40, and we need to have a zone in here. Maybe we want this to be 80 for our high side. So now we have our 40/80 in there. Press to accept. Go back to our main screen. Now we can see it's going to be 40 before the valve opens up on the low side. It's going to be 80 before it opens up on the high side. We're going to demonstrate how the valve actually opens up. So what you see here is in relation to what the cylinder is doing under the water, opening up the butterfly valve in here. So let's look at the vacuum gauge here and watch the cylinder at the same time so you can see what actually happens under the water. As you can see, our vacuum is in the green zone. Our cylinder is fully closed. Our vacuum is starting to increase. Once it starts to get into the yellow zone, you can see our cylinder is starting to step itself open. Our vacuum now is starting to drop. It's let enough water coming in to the suction side of the pump, diluting the mixture in the pipeline. Our vacuum is starting to drop. Once our vacuum starts to drop, again, now we can start closing the valve. We're going to simulate here a condition where you start to have a cave-in where material starts to fall in on the cutter. Our vacuum is going to start increasing rapidly and then get into the red zone. So here our vacuum is starting to increase. As you can see, it's increasing rapidly. Our valve is stepping open, but our vacuum has increased so rapidly we had to get into the red zone. As you can see, the valve immediately fully extended itself. Getting the valve fully extended, starting to pump the material away from the suction or the cutter of the ladder. The vacuum is continuing to drop. We're diluting the mixture in the pipeline. As a result, the vacuum is dropping. Again, once we're into the green zone, now we can start to close the valve back up. As you can see, the cylinder is now stepping itself back closed. The velocity reacts the same way as our vacuum, except for with velocity, as our load increases, we start to decrease our velocity, our feet per second or our meters per second. So as we start to load up the pipe, our velocity starts to slowly decrease. Again, the valve is closed because we're in the green and the turquoise ranges. Our valve will remain closed. Our vacuum is steadily dropping. Once we get into the yellow zone, our valve starts opening up, introducing fresh water to the suction side of the pump. Once it's opened up a ways, our velocity now starts to slowly increase. Once it gets back into the green zone, now our valve can start to close itself back up. It's indicated by the closing light here. Once the valve is fully closed, notice the green light just came on. That's an indication that the valve did fully seat itself closed. The pipeline discharge pressure simply has the green area and the red areas as we described earlier. Let's simulate a condition where our pump is just about wanting to cavitate because of a heavy load in the suction side. Our discharge line pressure is dropping, got into the red zone. Our valve instantly opened up to prevent the pump from cavitating. Once we got fresh water in the suction side of the pump, our discharge line pressure is going to start to increase. Once it increases back into the green zone, we can start to close the valve back down. As we explained earlier, our green zones represent good production going to the plant. When all three of these gauges are in the green zone, we see a light lit up here called maximizing. So the dredge operator knows that he should be now maximizing his production. Let's make an assumption his vacuum starts to drop. Dropping in the vacuum represents low production. We're into the turquoise range. Now we're flashing vacuum. The operator now knows we got a vacuum issue that's causing low production. He can look right here. I'm in the turquoise range. He either lowers his ladder or moves his winches to get more material in front of the cutter. The vacuum again starts to increase, and now he's back to maximizing his production. The same thing happens with velocity. If his production starts to fall off, the velocity is going to start to increase. Once the velocity increases into the turquoise range, representing low production, the operator sees velocity flashing at him. Once he gets more material in front of the cutter or the suction of the ladder, the velocity starts to drop back down. Once we're back to the green zone, representing good production, our maximizing light is now back on. As we can see in the lower portion of the screen, we have a yellow calibration waiting light. The valve is saying, hey, I need to calibrate myself based on a change in hydraulic oil temperature. Whenever the hydraulic oil temperature changes 30 degrees or more one way or the other, or change in Celsius, it's going to illuminate this calibration waiting light. What we have is a standard cylinder that is under the water. It has no way of telling the operator what the position of the cylinder is. There is no underwater electronics in this cylinder. So what we have to do is go through a calibration process so the computer knows how much oil is being introduced to that cylinder with each one of these segments when the cylinder is opening or when the cylinder is closing. And when we have a change in oil temperature, you will see this calibration waiting light come on. The calibration process is automatically engaged once the vacuum and the velocity reach the turquoise color ranges. So we can see our vacuum is dropping down into the turquoise range, and also our velocity. Our valve immediately opened all the way up. You can see on the gauge. Now the valve immediately closed all the way, and now it's starting to step itself open. It is starting to count how many of these steps it takes to go from fully closed to fully open. As you can see, the cylinder is constantly stepping itself open. Once the cylinder has fully extended itself all the way, it will automatically reverse directions. You can see our valve position counting up. The cylinder has now reversed itself. You can see it's starting to close down. It counted how many of these segments it took to open. Now it's counting how many of these segments it's taking to close. Okay, it just closed up. So what happened here is it calibrated and says it took 17 segments, the 17 here, to fully open. Once the calibration process has finished, we can now see the calibration OK indicator is here. When the calibration process is going on, the dredge operator needs to make sure that the parameters of the vacuum and the velocity stay in the turquoise range. So once that calibration process is energized, he needs to lighten up his load by lifting up the ladder for just a few brief moments until that calibration has completed. In this situation, we're going to demonstrate what happens in the calibration process in the event the vacuum or the velocity would get into the yellow ranges once the calibration process is started. So for the process to start, our vacuum has to be in the turquoise, our pressure has to be in the green zone, and we're going to start to bring our velocity into the turquoise. Once that starts, our calibration is now in process. Let's assume the operators continue to pump material and our vacuum is starting to rise and starting to get into the yellow zone. Once the vacuum is in the yellow or the red zone, we get a message that says calibration failure. In other words, the vacuum maximum limit has exceeded. So once we got into that yellow zone or higher, our calibration process has stopped. We're going to say OK to this prompt right here. And now notice we have a calibration failure light blinking. What we're going to do is have the operator pull up on the ladder and get the valve back into the turquoise range again in both areas and allow the valve to start closing itself back down. Once the valve has fully closed and both of these must remain in the turquoise range, in other words the operator has lightened up his load, he's going to press the calibration fail button to activate the calibration process. The valve immediately opened itself all the way open, and now the valve has fully closed itself, and the valve is continually going through the calibration as far as stepping itself open. It's going to keep opening up all the way. Once the valve is closed all the way, as you can see, now our calibration is okay. Now the operator can go back to pumping. This procedure of calibration is only going to happen once our oil temperature has changed more than 30 degrees. One of the features the Dredgemaster system has is the valve will continue to open and close in the event one of these three gauges would happen to fail, assuming that maybe we would have a vacuum transducer would fail, a velocity meter that would fail, or a pressure transducer fail. The valve will still open and close off of whatever the other two parameters are. So let's make an assumption, first of all, that the velocity meter would happen to fail. Let's go to the setup button here in the lower right hand corner. We have what we call our fail-safe offsets and our fail-safe triggers. With the case of the velocity meter, we've got our fail-safe trigger set at 3 feet per second. This also could be in meters per second. Assuming that the velocity meter no longer works or a velocity drops below 3 feet per second, our fail-safe offsets are going to come into play. As we can see here on our vacuum, for example, we're going to look at, assuming our velocity meter has failed, our fail-safe offset on the vacuum is going to be reduced by 1. In other words, right now we have the vacuum to trigger rapidly open at 25. If the velocity meter would fail, our vacuum now is going to be less 1. In other words, it's going to rapidly open at 24 instead of 25 because we're reducing it by 1. Our slow open is going to also be reduced by 1. So right now our valve is going to start to slowly open itself at 20. In this case, it's going to open up at 19, 1 less. And our slow closed, or the area from our green zone and turquoise areas, currently is set at 17, and this is going to increase to 18. It's going to be an additional 1. So if we go to our main screen and demonstrate this, our vacuum meter currently is working, but let's make an assumption that our vacuum meter now has failed. We're below our 3 feet per second. The valve first opens itself up because it thinks we've got a problem, and then it says, okay, we're in what we call velocity fail-safe mode. So the valve closes itself back up, and let's allow the valve to fully close, which it has. Now notice our green zone has narrowed up a bunch. We are now opening up this valve at 19, remember, instead of 20. So the valve, let's say our vacuum gets to 19 and above, you can see we are stepping the valve open and closed, even though our velocity meter has failed. If we get the velocity or vacuum drops, we get back in the green zone, then it will again close up. So we lost a third element here, so that is the reason why we're narrowing this band up a little bit, to give a little more protection, because we don't have the velocity meter to back us up in this particular instance. To change our fail-safe offsets, you simply would touch the square. Maybe we decide that 1 is too great. So if we would enter a half, for example, in here, on each one of these, then in this case our rapid open would start at 24 and a half, our slow open would start at 19 and a half, and our slow closed, or our green turquoise range, is going to start at 17.5 because we're at a plus here. Once we made this change, we need to press to accept the new recipe right here, and then we can go back to our main screen and notice how that changes. We have a little nicer green zone area there, but yet, even though our velocity meter has failed, our valve is going to continually to work off of whatever the vacuum transducer is asking it to do. Our fail-safe triggers are also easily adjusted. If maybe you want your velocity to trigger at maybe 2.0. In other words, if our velocity drops below 2, then our fail-safe mode is going to trigger at 2 feet or 2 meters per second or less, is going to trigger the fail-safe parameters to engage. Let's say our vacuum transducer failed. Anything less than 2 inches of mercury or 2 centimeters of vacuum, it's going to trigger the fail-safe to be engaged with the vacuum. And we can demonstrate that by simply reducing our vacuum below 2. That's assuming our velocity meter is going to start to work. Get our velocity meter up and working, and let's say we got a transducer in our vacuum that has failed. Once we're dropped below 2, give it about 5 seconds. Now our vacuum fail-safe mode has kicked in, which has reduced our green area here. It's going to open up the valve just a little bit quicker than what it did before. But our valve will continue to operate off of velocity and pressure. So as our velocity starts to drop and gets into the yellow zone, our valve is going to start to open up. As soon as our velocity starts picking up speed into the green zone area, it can start to close itself back down. So our valve continues to now work off of velocity and discharge line pressure. You can change any of these fail-safe offsets by simply touching it and entering in whatever value you want. Just keep in mind that, for example, let's look at pressure. Our low pressure now is set at 40. If we fall into a fail-safe mode, our pressure is now going to trigger opening at 45 because we have a +5 here. So that means we're going to add 5 to this. Same way in our high pressure. We're at 80 and we are going to then reduce our high pressure by 5, narrowing up our green band in the event of a fail-safe mode happening. The fail-safe triggers can be triggered by vacuum transducer failure, a velocity meter failure, or a pressure transducer failure. As you can see here, we're running on recipe number 1, which is all these color set points is recipe number 1. Let's assume maybe we add some pipe to the discharge of the dredge, or we go at a different digging depth, or we have a totally different type of material being pumped. One of the options the dredge operator has is assigning those different conditions, whatever it may be, to a different recipe. So what he can do is select recipe number 2, for example, by touching the up arrow. He's going to select recipe number 2, and you're going to wait for about 5 seconds, and it's going to give you a prompt, accept as current recipe, and we're going to say yes because we want to go to recipe number 2. And as you can see, all the color zones have just changed. The recipe 2s had different parameters than what recipe number 1 had. Let's say we want to change the recipe number 2 parameters a little differently than what they currently are. We simply go to our setup button, and again we can adjust whatever we want for our different recipe parameters by simply touching it. Say we want it to open up rapidly at 20 instead of 21 like it was. So we made that change. We are on recipe number 2. We need to press that button to accept the new changes, and we have now set up a change in recipe number 2. So the operator has the ability to select different recipes instead of going in and making all individual changes to the color parameters. One of the buttons we have in the lower left hand corner is currently we are running in auto, which the valve is going to automatically open and close based on what, if it gets into the yellow back into the green, it's going to open and close. If it gets into the red zone, it's going to fully extend. That's the automatic portion of the valve. If we want to open the valve manually, we're going to touch this auto button, and now we get a manual light coming on. We get 4 other buttons that now have appeared in the valve position gauge. For example, if we want to step this valve open a little bit at a time, we would simply touch step open. It opened a little bit. We can continue to step open, and we can fully open up the valve if we so choose by stepping the valve open. We can also step the valve closed by touching it and stepping the valve closed. If we want to rapidly fully extend the valve open all the way, we can hit the rapid open button. We have now just fully extended the valve all the way. And if we want to rapidly close the valve, we touch the rapid close button, and now we have totally closed the valve. If we want to go back to automatic mode again, we simply touch this manual button to auto, and now the valve is in automatic mode. If we increase our vacuum up there on the vacuum gauge, we can see that we're in the yellow zone. It is now triggered automatically based on your color zones. 99% of the time your operator will be running in the automatic mode. Okay, the valve has the ability to increase or decrease how fast you want the valve to open. Right now the valve is set to open at 14 segments. So it's going to take 14 of these hits to go from fully open to fully closed. Let's say we want the valve to open a little slower, or we want more segments for the valve to open up. We want to increase that 14. We're going to touch the setup button here, and we're going to go to our valve button down here at the bottom. So we're going to touch our valve. We are now in our valve configuration screen. The valve, when it opens up for 1/2 of a second, and then it stops. Our cycle off time is for 1 second, and we are opening at 24.4% force. In other words, the voltage to our open coil is getting 24.4% of the total voltage capable of opening the valve. If we want the valve to open a little slower, we are going to decrease our force percentage. Right now our force percentage is 24.4. Let's say we want to get more segments. We want this to be maybe 17, 18 segments, so we're going to give it less force each time the valve opens. So we're going to change this to 22, for example, and hit enter. Now we're going to go back to our main screen, and we're going to have to let the valve recalibrate. So the dredge operator is going to simply lighten the load up so that the vacuum and the velocity and the discharge line pressures, the valve is now calibrated in the calibration process, and it's going to set up a different amount of segments. It should set up a higher number of segments. As you can see, the valve position is counting up. It's continually counting. It's still counting up here. It's at 10. Before it time it calibrated, it set up 14. Now we're at 15, 16, 17, 18. Okay, now the valve set up 18. Now the valve is going to start to close itself back down. And once the valve fully closes itself, the calibration process will be completed. Okay, calibration okay. Now it's going to take 17 hits to fully open up the valve. In other words, it's going to take a little longer for the valve to go from fully closed to fully open. As you can see, our force percentage has changed. The computer automatically set up the percent of force to get 17 segments going open, and it automatically calculated what percent of force it needed to go closed, so that if it takes 17 segments to open the valve, it's also going to take 17 segments to close the valve. And that's the difference in our force percentage. A hydraulic cylinder uses less oil going closed than it does going open, due to the fact you have the area of the rod inside the cylinder taking up volume, so it has to move less oil to go closed than it does in an open. So that's where the computer automatically made this calculation and saying if it takes 17 segments to open at 21.8% force for 0.5 seconds each time it tries to open, it's going to have 12.1% force to go closed each half a second, so that we get 17 segments going closed. The other option we have is what we call our 2-speed option, or our second option, our slow fast set point. Currently our fast set point is set at 0. As you can see, this red line down here is down at 0. If we, for example, put our fast set point set at 25%, our red line climbs up to about 25% of the way of our valve position. Now what the valve is going to do is, instead of opening up at a half a second and stopping for 1 second, it's going to open up for it's going to open for 1 second period, and then also stop for 1 second. As long as the valve is under between 0 and whatever your 2-speed set point is. So once we change the 2-speed set point, the valve needs to recalibrate itself. So we're going to go back to our main screen. The dredge operator is going to lighten up his load again. Notice we have the calibration waiting light that automatically comes on because we changed that 2-speed set point, so it's going to want to go through its calibration process. After the calibration process is completed, we'll demonstrate how the valve is going to open up more rapidly between 0 and our 2-speed set point. So as our vacuum starts to increase, once we get into the yellow zone, you can see the valve is now opened a lot rapid. Once the valve has calibrated itself, we'll demonstrate how the valve opens more rapidly from fully closed to our 2-speed set point, and from our 2-speed set point on, it will go in a slower mode. So our valve opens up twice as fast. Now once it gets past our 2-speed, it again goes at the rate it normally would. The reason we have a 2-speed set point is the characteristics of a butterfly valve is when it first starts to open up, it lets very little water through until it gets about 25 to 30% of the way open. Then each segment that it opens or closes is more dramatic in the amount of volume that is being let through the butterfly valve. So that's one of the reasons why we put the 2-speed in there, is to allow water to be introduced in the freshwater pipe more rapidly to make your vacuum or your velocity reactions a little bit quicker. Next we have our hydraulic pressure indicator set points. These are the pressures that the computer puts in there when it goes through a calibration process. The first thing in a calibration process is the valve fully opens up all the way and records its relief pressure. It puts this in right here, the opened indicator, or the open relief pressure. The next thing the valve does is fully closes the valve and it records the closed indicator pressure. Then it starts stepping itself open. That step open process during the calibration records what the pressure is during the step open. When the valve reverses itself and starts to step closed, it records the closing set point pressure. The closing set point pressure is usually higher than what the opening opening indicator is. The reason again is we have less volume of square inches or square centimeters inside the cylinder going closed than what we do open, so it takes more power or more pressure to close a cylinder due to the decrease in volume of the cylinder going closed than what's going open. So this is very common to see your open indicator pressure to be less than what your closing indicator pressure is. Your opened indicator pressure and your closed indicator pressure should be pretty close to the same. As you can see, we're 781 relief pressure on the open side. We're 780 pounds of pressure when the valve calibrated going closed. The other thing we have is our calibration reset delay. We talked earlier about the computer wants to calibrate due to any 30-degree temperature change. It will automatically go through a calibration. We also have the ability to set the calibration frequency here. For example, let's assume that our oil temperature is changing less than 30 degrees. The computer will automatically calibrate within 1 hour if the valve has not completely opened and completely closed during that hour period. It will want to calibrate within the 1 hour. Let's say, well, I don't want it to calibrate that frequently. Let's say we wanted to maybe calibrate once in 3 hours. So we can enter 3 in here. Now the computer is going to wait for 3 hours before it goes through the calibration process, unless your oil temperature has changed more than 30 degrees in one direction or the other. Then it will still calibrate based off of that temperature change. But if the temperature change stays between the 30 degrees parameters from the last calibration, then it is not going to calibrate again until 3 hours, until the valve fully opens or fully closes. If it does do that within the 3 hour period, then the 3 hour resets itself. So it has to wait another 3 hours after the valve is fully opened or fully closed before the valve will calibrate due to this reset delay. From the valve configuration screen, you can also select manual, and you can step the valve open or step the valve closed, or rapidly open the valve or rapidly close the valve from the valve configuration screen. If for any reason the operator wants to calibrate the cylinder, he feels maybe the accuracy of the position is not accurate in relation to what the position of the cylinder is under the water, the operator can simply touch the calibration OK. Now we're in calibration waiting. As you can see, we're in the green zones here, so once the operator lightens up the load, gets our velocity into the turquoise range, and gets our vacuum into the turquoise range, and now we'll start the calibration process. The Dredgemaster has some setup parameters for each one of these transducers. To get to those, you just touch the setup button and go to the analog tab at the bottom. Select analog. Here we're looking at the pipeline vacuum gauge transducer. All of these set points, which is our upper scale limit, tells us that the vacuum transducer has the capabilities of going to 30 inches of mercury, and the lower scaling is 0. So basically this transducer goes from 0 to 30 inches of mercury is the setting of this vacuum transducer. Our velocity meter has the capabilities of reading 0 to 30 feet per second in this particular case. Our pipeline discharge pressure gauge has the ability to read from 0 to 260 pounds of pressure. Our hydraulic close and open pressure transducers are rated from 0 to 3,000. Our hydraulic oil temperature has got a rating of 0 to 300 degrees. And if you have the optional depth transducer, its ranges is from 0 to 60. The raw analog value is the value that's coming from each transducer. This tells us what our raw data is. Our scaled analog value is the actual reading of the transducer that you see on your main screen. So for example, right now our main screen on the vacuum is 16.9 inches of mercury. Our pipeline velocity is currently at 14.3, and so on. From the analog screen, you can also change how bright or dim you want the screen. 7 is the brightest setting. If you want to dim your screen, you can just touch your down arrow to dim it, and to brighten it, you touch your up arrow. To change your time on your main screen, if you want to change the hour, you can simply touch the up arrow, which changes the hour, and change the down arrow to decrease your hour. One of the features that this monitor does not have is the ability to change the minutes and the date. To do that, you simply need to press and hold on the upper right hand corner of the screen. You're going to get a message that says activating system screen will stop the panel run mode. Simply hit the OK button. We're going to then go into our main menu, which is our settings. Touch the settings, And here we can adjust the clock right here by touching this button. So if we want to adjust the minutes, for example, we're going to touch the right arrow, and right now we're set at 13 minutes. If we want to increase it by a minute, we touch that to increase it. We want to touch the seconds, we can decrease or increase the seconds. To change the date, you touch the right hand arrow on the date. You can change the month, the date, and the year by simply using your up and down arrows. Once you've got those set the way you want them, and you can see what time you got as well in a clock here, you simply hit the OK, and then you go back to your main menu right here, and then you hit the exit button, and now you're back to the analog screen. If the Dredgemaster system failed a calibration, the operator can go into the Alarms tab by touching the alarms, and he can read what has caused the calibration to fail. For example, it gives you the date, and let's look at by touching the line down button, I can go into a fault that happened on 11/3/08 at 8:02 a.m. Calibration faulted or failed due to the valve open sensor failure. So if you have a bad transducer, you can use this screen to diagnose a open or a closed pressure sensor that was causing the fault on the calibration. If, for example, on the top, if we go to line up, we can see here where the reason for the fault is a maximum vacuum exceeded. For example, the unit was trying to calibrate, and the operator probably didn't catch the calibration in progress quick enough, and the vacuum spiked up into the yellow area of the vacuum gauge, which caused the calibration to fail. So here it says maximum vacuum exceeded, which would be that. Periodically, you'll want to clear all your faults, and you'll touch the clear all button. If you want to look at how many alarms you've had, your alarm count, this keeps track of how many alarms that you have had over the period. You can page up or page down and look at all your faults that have happened. This is a troubleshooting guide. To get out of the alarm page, you hit the exit button, and you want to get back to the main screen, you just touch main. For those who have purchased the angle and the depth option, for these to be accurate readings, we need to go in and set up the depth calculations. Go into the setup screen, go into your depth tab down at the bottom. We have all the dimensionals of your ladder that needs to be entered in here. So basically, let's look at dimension number A, which is coming off the end of your fish mouth and to the hinge point of the ladder. Currently, we are at 48 feet. Let's say on your particular ladder, maybe that's 55 feet. So you just touch that square, you enter in 55.0, hit enter. Now that dimension from the fish mouth to the hinge point is 55 feet. Same thing you would do is from the fish mouth end to the center line of where you mount the depth transducer on the ladder. That dimension is going to be entered into here, and let's say that may be 17 feet. So you enter 17.0, enter, and you continue to put in all those calculations in each one of these squares. This top one, letter C, is the height of your hinge point to the water level. So that is what dimension C is. Once you get all those dimensions entered in, what your operator is going to do is lower the ladder down into the water, as you can see down here. Once that is lowered, it's going to give you what the calculated depth is. Before the operator lowers the ladder down, what you need to do is attach a tape measure to the lowest point of your cutter down here and pull the tape measure to the water level. For example, the calculated depth may be one thing, but the actual measured depth may be something totally different. So to get the calibration correctly, leave the ladder down in the water at whatever depth you want, as long as the transducer has to be under the water a ways. The deeper the better that you're going to be digging at. Lower it to that depth and then measure what the actual tape measure says. And if what the actual tape measure gives you, you need to enter in as M. That will be the tape measure reading right here. Once that is completed, the operator can then raise the ladder back up and out of the water and remove the tape measure. The key is make sure to keep the ladder at the depth when you enter in this value. Don't let the ladder come back up and then enter in value in. Make sure the ladder stays down under the water at the depth you're calibrating at, or what the depth the tape measure reads, then enter in this amount. For decimal conversions, you can 7 inches, for example, equals 0.583. So if one of your dimensions in here has a 1 inch, 2 inch, 11 inch, whatever, you can look at your conversions here. Also, this is a guide that explains what each one of these dimensions is. A, B, C, D. They're all explained right here on the side. Once all the dimensions of the ladder have been entered and the calibration value that the tape measure read has been set, you'll find the angle and your depth to be very accurate.